All right. Well, I think it is time for the very final lecture of this course. Before I begin, sort of trying to tie up everything we've been talking about this whole semester, let me start by telling you a little bit about just where grading stands, because I know I've gotten some emails about, how whether I could predict people's grades or do some kind of projection for them as they try to decide whether to do credit, no credit, that kind of thing. So the first thing is just a review of what's still outstanding. Tonight, all y'all are submitting questions for each of the presentations. In total, the presentations take something like a little under 3 hours to watch. Though I should note that Canvas comes with a little speed adjustment dial if you're really delayed it way too far. So I'm asking you to ask one question of each presentation. I've looked through some of the ones that have been submitted already, and I'm impressed by how thoughtful they are. So I'm hoping that that's going to be a joy to all y'all when over the next 2 days you will write written responses to the questions your classmates have asked of your presentation. These responses don't need to be that long. I'm not expecting you to sort of write a thesis on each of them. And questions that ask you what would happen if you do this, I think you should read those as, please speculate. Again, this is sort of emulating the experience you would have giving an in-class presentation. So nothing more than a couple of sentences worth of response is really expected for you. So the questions are due tonight at midnight. The answers are due Thursday at midnight. Also due tonight is the extended deadline for submitting the project code itself. And looking over y'all's presentations, it looks like a lot of you were definitely leveraging those extra days to finish verifying Quicksort. So best of luck to you. I'm going through and grading the final presentations kind of as we speak. So I am hoping to have the presentations and the project code and the Q&A, everything graded by the end of the week. If you are trying to figure out what your plausible grade will be, it is currently looking like we'll use a pretty standard grading rubric, like 90s, 80s, 70s, etc. Credit will be credit/no credit will work in a similar way. It'll be somewhere in the 60s. Not 100% sure where, but most likely y'all will free me of the responsibility to decide where in the 60s exactly the credit, no credit bar should go. If you want to figure out what your grade is likely to be, the grade is 40% assignments, and those are almost entirely graded, except for some very late submissions. 50% project, so approximately half of that is in already, and 10% participation, which isn't correctly reflected on Canvas. I'm working on it, but is just half class attendance back when we had class to attend, and 50% submitting those feedback forms that y'all loved so much. Asterisk on the loved. So currently, it looks like everyone who asks for credit, no credit, will probably get credit. That's not a guarantee by me. I'm just saying, looking at the grades, summing them up, it looks like you'll all end up above the bar, any reasonable bar where credit, no credit would go. So I know many of you are thinking about that possibility. I've been told varying dates about when you need to decide that, but some of the dates I've heard are today. So maybe look into that if that is something you're interested in. I have been told by the School of Computing that we will do everything possible to not count credit, no credit against you, including allowing credit, no credit for course requirements and so on. But if you're concerned about any aspect of your sort of school trajectory or course prerequisites or whatever, do get in touch with the graduate and undergraduate counselors. I'm sure they would love more emails today. So any questions about the grading before we move on to sum up the course as a whole?
I just had a quick question for submitting the code for our project. I can submit the entire project or just like the relevant source files.
I'm not
What was
planning
the-
on like building and then I'm planning to read it. So sending just the relevant parts, the parts that you did, and details of any tests you ran it on, any evaluation that you did. Like I basically want to know that you actually did the stuff you said you did in your project, and that it looks like it was a serious effort. We're not looking. I'm not looking to sort of meticulously grade this for style or quantity of comments or anything like that.
Okay, cool.
Yeah. So if you're working within sort of a large existing framework, send the diff, I guess, or your subdirectory or whatever the case may be. And the code submission asks you to include a README, and for your project, I think in the README maybe point to like what project you built it inside of and so on.
Great, thank you.
Okay, any other questions about grading? Excellent. I know grading is a perennially beloved topic at this time of year. So if you have last minute questions, do feel free to email me. And with that, let's talk a little bit about what it is that we've covered throughout this whole course. So just to kind of jog your memory about what it is that we did this whole time. We started off with this kind of pretty simple definition of what we wanted out of software verification. We wanted no bugs because bugs are bad. And we start on sort of a journey of trying to figure out how we can achieve no bugs in our software. And I said that there's kind of three parts to this journey. First, before you can conclude that there are no bugs, you need to first determine what is a bug. So the first part of this class talked all about specifications, how to write them down and how to reason about specifications, whether one specification implies another, whether a specification can be true, that kind of thing. Well, then we wanted to take this sort of abstract reasoning about specifications and tie it to a concrete program. Take an actual implementation and show that it meets some specification. So we developed all sorts of techniques to do that, core logic and symbolic execution and so on. And then finally, we talked about how to take these ideas and scale them up by casting them in a different light. So we looked at abstract interpretation, which is sort of a way of taking core logic and pre-computing parts of it so that you can do the analysis more efficiently. And we also looked at dependent types, which takes kind of the opposite approach of giving you a very powerful language where you can mix the proof and the program into one sort of coherent system. So in particular, we looked at logical reasoning, we looked at program logics or Hoare logic, and we looked at several techniques for static analysis. So this was kind of this broad overview of what we wanted to achieve and what we achieved in this class. And specifically, we can dive a little deeper into some of the techniques and technologies we've learned. So first, we did a deep dive into how do we do automatic logical reasoning. We started with this generic language for writing down specifications called first order logic. And then we said that we talked about a whole pipeline by which that first order logic can be converted into something that machines can reason about. So first we talked about removing quantifiers through a variety of techniques, then converting this unquantified thing into conjunctive form. Then we discussed an algorithm called DPLL to form this conjunction of literals. Then those literals we split up between different domain-specific solvers. And finally, we did some domain-specific reasoning about each of them. And so we covered techniques like quantifier elimination, the Tin transformation, the DPLL algorithm, and the Nelson-Hoppen mechanism. Now, I understand that the details of some of these might be hazy by now. There's not a final, so you haven't been forced to review them. But some higher level ideas, hopefully, remain. You remember this broad idea of quantifiers being a challenge for logical reasoning. You remember the specific sort of high level ideas behind DPL, kind of this idea of taking a look at the query and making all necessary choices and then making reasonable guesses and seeing if they're possible. And also these ideas about splitting a generic question across sub-questions, each of which relate to one particular kind of thing in the Nelson-Oppen mechanism. We also talked about some different methods of domain-specific reasoning. We talked about model building, and we showed how that's useful for reasoning about equality. We talked about variable elimination and how that's useful for reasoning about integer inequalities. And finally, we talked about translation to some lower level theory. And we looked specifically as to what that might mean in the case of array reasoning. So in short, we've covered a bunch of, we've covered first this generic pipeline for transforming high level specification to simpler and simpler pieces. And then we've also talked about some ways in which you can answer queries about specific logical properties, ways that show up in all sorts of other domains that you do reasoning about. But this was all talk about abstract logical properties, abstract specifications. What we really wanted to do was tie this specifically to the task of verifying programs. So what we set up was this idea that you could take expressions in the program and convert them into logical formulas, expressions in those logical formulas and potentially side conditions that make those expressions valid. And then we talked about how we could write down generic predicates, properties of the environment of the variables in scope at a particular part of the program. And then this, how we can describe the behavior of a program by describing the predicate before and after. So we had this Hoare logic PSQ idea, which is that if P is true of a state and you execute a statement S, then Q is true afterward. And what we discovered is that there are mechanical ways of converting these Hoare logic formulas into specific logical queries that we could send to the solvers that we spent the whole first half of the class discussing. So this is our core idea of how we could tie programs to their specifications, using the text of a program to convert the specification bit by bit into a single logical statement, what we call a verification condition, which basically tells you, does this program satisfy this spec? And in the process of doing this, we covered some tricky things that come up when reasoning about loops, like we had to do that whole thing with invariance, or functions, or we talked about how pre and post conditions are reused, and even this idea of separation. And then once we'd discussed this broad idea of taking specifications and tying them to the program, we started looking at ways to kind of twist these ideas a little bit to make them fit a different context. And the first one we looked at was analysis of larger programs, but in a task-specific way. So maybe you don't need to verify a generic property of a program. Instead, you need to verify a particular property, like the absence of array out of bounds exceptions. Well, we talked about ways how we could take this task-specific analysis idea and instantiate it by creating a set of specific conditions about variables or program states that we wanted to track. And then talking about two functions that we need to implement for these conditions. First, a merge function that takes two possible states and converts them into one. And then what we called a transfer function, which represents the behavior of some program primitive as operating on these abstract conditions. And in some sense, you could view this whole thing as taking Hoare logic, what we just discussed, and specializing it to the case where we have not arbitrary logical expressions, but a finite set of conditions. And the reasoning about those conditions follows rules we derived from logic, but allow us to avoid redoing logical reasoning and going through the whole thing of talking to the solver. So that is one way that we saw of taking these ideas of Hoare logic, but eliminating the solver. And then we went into the opposite direction and talked about a different technique, type dependency. Instead of building the solver in some sense into the analysis, it builds the solver in some sense into the language. So we talked about how we can introduce this idea of type constructors and induction principles which you could also call introduction and elimination rules, and how you could use those both to define new data types, but also new properties that you might want to prove of that data type. And finally, we talked about how this idea of propositions as types, which is that things you might want to say about values are really kind of like types whose terms are proofs of that proposition. And so we went further and talked about ways that we could use a language imbued with this philosophy to add information, like discussions, for example, of length, into the type level of a list, so that your program's type checker can do the work of ensuring that your program behaves correctly. For example, that it doesn't have array out of bounds exceptions. So at a high level, this is our whole scheme. All of the different techniques we've covered, the different ideas that we've explored in this class, and how they relate to this central task of verifying that a piece of software is correct. But let me now take a moment to zoom out and try to extract some broader themes that you might take away from this class. Some ideas that ran through the whole course and form kind of a part of the perspective that this course applied, something that you could take away into your future work, your future career, your future academic life, other classes. The first is this idea of the program as an object. We usually think of programs as being something you run. Programs are the actors, they do stuff. They consume data, they cause events to occur, they access a database, they interact with the user, whatever it is. We think of the program as the subject. But in this class, we've instead talked about programs as the objects, where programs are something you compute over, your computer reasons about. And this makes sense. For any one program, there's all sorts of things you might want to do to it. You might want to auto-format it, or type check it, or fuzz it, or use symbolic execution, or go all the way to generating verification conditions and then testing those with an SMT solver. All of those independent steps rely on treating the program as something you compute over, not something that does the computation itself. And in particular, you could see that because none of these require specifically running the program. So this was sort of a theme running through the whole course, and we've seen all sorts of different computations over programs. And basically, you've seen this if you've done a solo project, you've seen this in your solo projects as well. The fundamental technique here is recursive traversals over this tree of objects that forms your abstract syntax tree. And in particular, during that recursive traversal, generating verification conditions, or checking static analyses, or checking types, or doing lattice operations, or whatever the different case for your particular program analysis may be. So I think this is the first theme of what you've seen. It's maybe a theme that you've seen carried over from a previous class, like in programming languages, but it is potentially also a theme that you can look at going forward. Hopefully you've seen that program as an object you can write programs that operate on. You can write programs that operate on programs, and you've done this a couple of times in this class, and you've seen how it's done. So hopefully this is a technique you can take forward. So questions, or perhaps just personal perspectives on this theme? Maybe then I'll do a quick poll by hand raising. This is a perspective you sort of encountered in your previous classes, or was this kind of new to you? So raise your hand if it's new to you. Okay, I'm glad. It's hopefully something that you'll see every once in a while will come in quite handy in your academic or career life.
So this is one idea, the idea of the program as an object. But we mostly looked at a more concrete part of this, which is the program as an object satisfying some kind of specification. It's a program as an object with properties. And so I want to talk a little bit about this other theme running through the class, which is specifications. If you think of a program as this long pipeline, then you've probably had this experience where the program does a lot of stuff, and at the end you realize that there is a bug. And now you're faced with the question of which part of the program, which of these different phases or subcomponents is responsible for this bug? Was it passed bad input? Did it validate it incorrectly? Did it store it in the database correctly? Retrieve it from the database correctly? Do whatever, whichever of these steps, which one was incorrect? And so the idea of a specification, that's fundamentally about describing a program's responsibilities. And in particular, describing what it means for a program to work correctly. And in this problem you might have, where a whole bunch of stuff has happened and now a bug has occurred, what specifications do is they set up barriers between each component or phase, describing what that individual component is responsible for, so that you can identify which particular components failed so as to cause this bug and narrow down to a specific place. It's really this aspect of specifications that is most important for verification. And you've seen this in your attempts to verify sorting algorithms, for example. At the high level, describing the goal of the program is easy. But describing the goals of each of the sub pieces of the program, the different helper functions that are invoked, or the responsibilities of each iteration of the loop, that's more challenging, but it's also essential because it defines the unit of analysis to be some small segment of code that can be independently analyzed. And as part of this theme, we've explored lots of different kinds of specifications in this class. We've looked at pre and post conditions. We've talked a bit about types. We've talked about loop invariants, and we've even mentioned effects. So overall, what we've looked at all sorts of different specifications you can write for components so as to delineate their responsibilities. And ultimately, the ideal here is that if you delineate the responsibilities well enough, you stop having to think about how a component is written unless you are working on that component, because all of the other components refer to the spec for their neighbors, for their responsibilities, and expect those components to fulfill their responsibilities than to reason out the actual implementation of that component. So this is, I think, another big theme. We spent the first part of the class just talking about how to write specifications, talking about first order logic, which is the language in which we state specifications. And then we've come back to touch upon this point over and over again, talking about pre and post conditions, weakest precondition generation, invariants, and then later we talked about things like dependent types. All of these form different kinds of specifications you can write down for a component. So any comments or questions or personal perspectives on specifications? Something you found interesting about the way we talked about them in this class?
One thing I thought was interesting is this class taught me to think of specifications as a like a first order logic statement, or not necessarily first order, but like a mathematically logical statement rather than like a documentation of things a program should do or a product should do. So I thought that was pretty cool.
That's true, yes. And so one thing we haven't talked in this course pretty much at all about is what you might call like weaker forms of specification. Most programs come with a manual of some kind, which is sort of like a specification in that it describes what the program ought to do. Many programmers have in their mind an idea of what the program ought to do. But one thing we've specifically talked a lot in this course is about taking specifications and turning them into something written and moreover formal, something that is concretely true or false and has no room for interpretation. As you've seen in this class, this is definitely hard work. There's a lot that goes into writing a specification. so that there's no room for error, there's no ambiguity, and nonetheless, it captures the behaviors you wanted. We saw that in the very beginning of the course where we talked about how do you even write down a specification for a sorting function. And we've seen that again and again as you've done various verification tasks of your own. For example, the symbolic execution you did for CLE required some comparison between the manual and the analysis to determine whether you'd miss something in the specification you developed or not. So I think, yes, that's a perspective, and it's hopefully one that turning specifications into something crisp and concrete, something formal, despite being a lot of work, can be incredibly valuable. Exactly because it makes it something that you can rely upon. Other comments, questions, perspectives?
I didn't really have a good mental image of just how hard it was to make one of these before this.
Yeah, I think the best, I think, there's like a classic like philosophy 101 class, right, where the professor asks you to like define a chair, right? And of course it's basically impossible to define a chair. It's like number of legs, unclear, can be sat on, you can sit on a lot of stuff. I think it's similar here. It's easy to say, oh yeah, I know what the program should do, but it's difficult to write down what it should do, especially in those edge cases. And actually, I think a lot of the value of software verification is actually in developing the specification itself. The verification step, which we often talk about as the hard part, is in some sense just there to check that you've written down the correct specification. And a lot of the real challenges in figuring out how do you even specify the behavior you want. Anything else? Any other comments, questions, perspectives? These are good, by the way. Okay. Well, so that's those are two maybe like very high level ideas. In some sense, they're ideas that we didn't even specifically discuss so much in this class as just filled the space in which we work. This idea of a specification and this idea of programs as our objects of analysis. A more concrete idea that we spent quite a bit of time talking about is this idea of an abstract execution. Basically, in order to analyze the program, any program, you need to run it, but not with specific input values, because there's usually an infinity or near infinity of specific input values, but with non-specific abstract inputs. So if you have a function that computes the maximum of two numbers, well, in order to determine whether or not the program is correct, we need to consider all pairs of inputs, all pairs of, for example, integer inputs, x and y. And even if your integers are, say, 32-bit, this is still way too many pairs to exhaustively test. So instead, we need to somehow run the program not with specific x and y, but with some kind of abstract x and y. And that means that as we do the execution, our values don't have concrete values, they also have abstract values, which now might be some kind of expression about those values. So the final result of a function or a loop body or anything else that we're analyzing is going to turn out to be an expression over these input variables, whatever those symbolic input values might be. And then another idea that ties into this is that the control flow path a program follows, which way it goes through an if statement, those are additional conditions, we call that a path condition, that tell you something about those symbolic values. So we have this tie between running the program with symbolic inputs, but also this idea that you have to go down all paths and that those paths tell you something about the symbolic inputs that went down those paths. So that's sort of an idea that we've seen a lot in this class, whether it's propagating weakest preconditions backwards, which still involves writing down the expression that you are computing and turning it into some piece of logic. Or if we were talking about symbolic execution or abstract interpretation, or any of the techniques we've talked about in this class. And then one thing that this necessarily requires is you're going to be checking things like implication or possibility or side condition as you symbolically or abstractly execute a program. You're going to need to determine, can this array access be out of bounds? Or is this path possible? Or does this imply that a certain condition will occur? And that's going to require logical reasoning just to determine whether or not this abstract expression or abstract condition must be true. So this is another sort of, I think, core idea of this class. I think it relates both to how you yourself understand programs. If you've written a program, you usually trace it through with some kind of symbolic values, just sort of run it in your head. And it also relates to how computers do the same task. You need to develop a data structure in which you can represent an abstract value and then propagate that through all the paths of your program. So questions or comments or perspectives on this broad theme of this class? I think this technique, and in general, the technique of sort of non-standard executions of a program, that's often exactly how you approach this idea of the program as object. Programs are fundamentally tied to their execution, but how you execute it on actual values or on symbolic values or on abstract conditions that might or might not be true, that's sort of up to the program, and is changing the interpretation of a program changes what you can learn about it. And I think finally, one quite concrete idea that there's a good chance you will make use of in your career is just this idea of domain expertise. So we talked a little bit about this when we talked about the construction of a solver for logical formulas, and specifically this idea of the Nelson-Oppen mechanism, which is in logical reasoning, you often have to combine different bits of domain-specific knowledge. So for example, if you want to test whether this expression could be true of some array and values x and y, you actually need to reason both about arrays and about integers. So we talked about a variety of techniques for taking this one query and splitting it now into several queries, which are decomposed, so that each of the different parts of the query can be handled by a different kind of solver, an array solver for this top line, and then an integer solver for these next two lines, for example. And this is a broad idea that comes up often in search algorithms in general. Often you're looking to take some problem that your program is trying to solve and then break it into smaller subproblems. And if you've taken an algorithms class, you've probably seen this in the guise of a divide and conquer algorithm, where you hope to recursively subdivide the problem smaller and smaller until it can be easily solved. But another way that this idea of decomposition comes up is the decomposition enables specialization. If you can break the problem into two pieces, you could solve those two pieces in two different ways. And you can apply different reasoning to each one that's tuned to the kind of problem you ran into. So for solving logical formulas, we did this in order to break a single logical query over multiple domain-specific solvers, so that integer reasoning can live in one place and array reasoning can live in another. But more broadly, this is useful for search algorithms of all different kinds. And specifically in the Nelson-Oppen mechanism, we saw something that comes up often when using this technique, which is you might split up the problem and solve each subproblem, but find incompatible solutions. And in the Nelson-Oppen mechanism, that incompatible solution meant that one solver would assume two values were equal, while another solver assumed that they were unequal. So in the Nelson-Oppen mechanism, we had this loop where you would first split the problem up, decompose it, and do some specialized reasoning about each subproblem. Then you'd bring them back together and detect incompatibilities. So those incompatibilities would cause you to fix up the subproblems. You would create new subproblems that reflected the equalities or disequalities that you wanted to achieve, send them back out to the solvers, and repeat this process. And this is a common technique in any kind of search where you break it into pieces. Those pieces, they might not be possible to stick together. And so you have to do a loop of recursively improving your specifications of each subproblem so that you can eventually find a solution to the complete problem as well. So any perspectives or comments about this particular idea, which I thought was quite a core idea, both from, by the way, this idea of this problem of reasoning about logical queries, but also for this problem about verifying programs, where again, we had to continuously do decomposition so that we can reason about the loop body separately from the function that contains the loop, separately from the other functions. So it's this core idea of decomposition and specialization shows up over and over again. So yeah, sorry, any questions or comments about this particular theme that occurred over and over again throughout the class? All right. Oh yeah, go ahead.
I was just thinking that like the idea of like decomposition and treating like a loop body separate from everything else, that just I thought it was interesting how it lined up with a lot of good software engineering practices that were taught a lot, like specifically separation of concerns. I think decomposition in general has been like a really useful skill to work on in my own. So it was nice. I guess it was interesting to see how that those concepts came, I don't know, almost to like the forefront of certain topics in this course.
Yeah, I think sort of a general idea that it's hard to really communicate in a class, but comes out once you've done a lot of verified software development is that good software is easier to verify. And this comes out in a lot of places. You try to separate concerns so that you could think about one thing at a time in your verification. You try to take effects and keep them in one part of the program because reasoning about programs without effects is usually easier. You might try to reduce dependencies between different components because dependencies mean more complex specifications about the boundaries. All of that, all of those techniques lead to more robust, resilient, and maintainable software as well. And is in some sense kind of this secondary value of software verification. In one sense, you can think of software verification as having your program read by a very meticulous but extremely stupid programmer, namely the computer. So if you can write your program in such a way that it is understandable, it is clear, even to an extremely stupid, granted meticulous reader, the computer, it tends to become more readable and more understandable to the programmer as well. Okay, so these were some broad themes that I hoped you extracted from being in this class. You've picked up on a perspective that you now take into future classes or into your work life. But this class has been not just about broad themes, it has been specifically about verification. So I wanted to, at the tail end of this class, just do a final bit where I talk a little bit about using the ideas of software verification in actual programs out there. Now, many of you have now developed verified implementations of Quicksort. And Quicksort was a breakthrough computer program in the 70s. But I think some of you may have questions, to what extent do these ideas apply to the actual world? Some of you are software engineers in your actual work life, and you might be thinking, these theories are cool. It is interesting to know that we could verify complex software, including some of the the more practical lectures that you've had in this class. But nonetheless, if you have an actual program, what are the steps toward verifying it? Well, it's not something I emphasized much in this class because I wanted to talk about the technicalities, the specific theories of how to verify a program completely. But verification is really a means to an end. The way I put this end at the beginning of the class is that the end is no bugs. And more broadly, you might describe the end being confidence that your program does not have bugs, because you don't just want your program not to have bugs, you want to know that it doesn't have bugs. So verification definitely gives you confidence your program has bugs. You have a specification and you've proven your program meets that specification. You've defined what a bug means and you've proven you don't have one. And that certainly should give you confidence that your program is correct. But there's really a spectrum of ways that you gain confidence a program is correct. The very loose end of the spectrum, there's tests. Now, everyone tests their code because while you are running the code, you, oh goodness, I hope at least try compiling and running it on some inputs. And if you work as a software engineer, most likely, well, cross your fingers, but most likely, the company you're at does some kind of unit testing as well, which is just a standardization of the process of testing your program, saving the inputs you run the program on and the outputs you expect, and making sure that it continues to have that behavior as it is modified. Testing gives you some confidence that a program is correct, which is why you do it before, say, submitting a program as an assignment. But I'm sure you've seen bugs in code that you tested before. In fact, this is sort of a common experience to all programmers. So let's talk a little bit about how you might go from a regime of simple testing and upgrade it bit by bit toward the direction of a verified program. So the first thing that you might notice is that when you're doing unit testing, your specification is non-existent beyond a particular set of input and output examples. So the first thing that you might want to do is write an actual specification. And once you've written a specification, you now have the possibility not of testing specific inputs you've written down, but testing randomly generated inputs. So I can give you an example of myself doing this in practice. A couple of years ago, I worked at Dropbox, which is a company that makes an app that syncs things across your devices. And one of the core algorithms in the Dropbox sync engine is this thing called the operational transform. It has to deal with inserts into an array being synced across multiple devices. Well, they had an implementation that had been written and rewritten several times over the years and had done some pretty extensive debugging. And the tests for it were a pretty long list. I think it was 500 different tests of specific sync scenarios that had to be tested. And I was tasked with improving our confidence in this further and decided to use some random testing. Well, the first goal was to write down a specification. What does it mean for this algorithm to behave correctly? And it turns out there's a theory of what exactly it should do. It, in effect, should enforce commutativity between certain operations. So we took the existing 500 tests and we replaced them with a tool, with a loop that would generate random inputs and check that they satisfied this specification. And all the tests that exist already could be generated by this tool, but it could also generate a bunch of tests that hadn't been written down. And this found a bunch of new bugs. For example, there was a line of code that said that read a plus equals 1, but should read a plus equals I. Easy bug to mix. I and 1 look kind of similar. But of course, in the one unit test that tested that line of code, I was exactly equal to 1. So it didn't pick up the bug. And this is the kind of value that random testing gives you. It removes the bias from choosing particular inputs, and it gives you a concrete specification for what the program ought to do. And that specification itself can be useful in developing other parts of the program. Moreover, it's not just a specification you wrote down in English in a documentation page that will go out of date. It's a specification that's enforced by your testing regime. So that may be the first step that you make toward improving your confidence in a program. But random testing has flaws of its own. In our previous lecture, we talked about a crypto bug where random testing would not have caught it because only 1 in every 10 to the 22nd tests actually fell down the particular bug that occurred. So in some cases, random testing itself will not be enough. And the next step is usually to characterize the possible inputs to the program as well. So that now you have a set of inputs that you can fully describe and a specification for what the program should do on each of those inputs. Once you've characterized what are the inputs to the program, you can start making sure that your random tester actually covers the whole space of inputs uniformly in some interesting way. Plus, once you've characterized the set of inputs, now you can see that certain inputs are edge cases, certain behaviors are unusual, and you can adjust the random tester to generate inputs not fully randomly, but in a way that would explore this space of potential bug identifying inputs in an intelligent way. In computer science, we often call this model checking, and one form of model checking is to exhaustively test every input. But even for programs where that's impossible, you can often identify what are the useful inputs to test. How can I make sure that every different kind of input or every different situation is sampled relatively often by the tester? One actually place that model checking of this form comes up and is quite powerful is fuzzing. A lot of fuzzing tools have been developed in the last couple of years, and it's become somewhat common in industry to use them for essential pieces of software. A fuzzer basically is a tool to randomly generate inputs from some space of possible inputs. So for example, you might want to generate random binaries and check that your JPEG parser doesn't crash when handling them or access memory out of bounds. So accessing the memory out of bounds, that's your specification. Binaries of a certain size with a certain layout, that's your set of inputs. If you do this naively, you just generate random binaries, the vast majority of them will be invalid in a totally uninteresting way. But if you can characterize the different paths that you can go down, the different kinds of inputs, the differences between that cause one input and another to be handled differently, well, that allows you to effectively search the space of possible interesting bugs so as to find the ones that actually occur in your program. So questions about these kind of first 2 steps where we're incrementally improving our confidence that this program is correct? Or actually potentially just examples of how you've done this in your own career. Go ahead.
Am I right in assuming it would be hard to describe the crypto bug that we talked about before using model checking as well?
That's a good question. My understanding, the way that bug came up was it was basically 2 different parts of the code disagreed about how to handle a specific edge case. One thought that one thought that inputs had to be in a certain format and one didn't. It depends on what exactly you mean by model checking. Certainly, if you took the end-to-end complete crypto library and tried to enumerate through all possible interesting inputs or dissimilar inputs, it'll probably take you a long time to find it, but that's because the crypto library does a lot of things. On the other hand, characterizing the inputs that each program expects, it may or may not have identified the bug, but having that characterization would itself, in effect, it would describe the precondition for each program. And so in effect, that would probably help identify that there's this mismatch between the caller and the callee. So we're still at the state of generating inputs and checking to see if things work, if the spec is satisfied on an example. So we're not yet at the point where we can actually guarantee anything about our program yet. We are at the space where we can We can start getting more confidence because we've tested more things. We think we no longer worry that we missed an interesting test, though we might still worry that there's a subtle bug that testing isn't going to find. Okay, so far what we've done, we've still been treating the program kind of as a black box. We're generating inputs, then we're running the program to see what happens. And what we've developed so far is a specification, a pre and a post condition, a description of the inputs, their format, what we expect of them. Now we want to continue gaining confidence in the program. And what we'd like to do is we don't think that there are common bugs anymore. We've explored all the interesting kinds of inputs. We've made sure to test a couple from each one, maybe a lot from each one. We don't think we're biased by making the same mistake in our tests and in our code because the tests themselves are dynamic. They'll explore the whole search space. But there's still edge cases or weird behaviors that come up extremely rarely that we might not be able to catch. So the next step beyond just characterizing inputs, generating inputs, and testing them has to come from looking deeper into the program itself. And so a place you might start is to try to check all of the paths of execution that your program satisfies. So symbolic execution, that could be one way that you think about this. That could be one technique. But more broadly, you want a sort of inventory of the different paths your program can go down, the different loops you might get stuck in, the different data structures that can be of various sizes. And you want to start making sure that each of the different paths through your program has been tested well. Because as you recall, in our discussion of symbolic execution, the program path, that describes a sort of condition on the inputs, a path condition on how you called the program so that it went down this path. If you can characterize all of your paths, then you can check that your characterization of the inputs is correct, that you actually have every different kind of input being every input that goes down a different path through the program. Now, in most programs, really, the set of all possible paths is infinite. But nonetheless, you can look at all paths of a certain size, you can bound loops. That is immediately going to give you more confidence because now you know that every sort of thing, every line of execution your program can have, you've checked that it satisfies the specification that you're interested in. Most often, what you find in this kind of step, where you're checking all the different possible paths through your execution, usually the sort of bugs you end up discovering are bugs in, for example, error handling code or exceptional situations, bugs in dealing with missing files or missing dependencies, bugs due to error codes that you didn't check for. Those paths are rarely executed, and in fact might not be executed for any correct inputs, but are often still essential for the correctness of your code. You wouldn't want an exceptional situation to grant a user access to something they shouldn't have or delete data that you wanted to preserve. And so in some sense, characterizing all the paths in your program, making sure to check all of the paths through the program ensures that you've handled even the edge cases, even the exceptional situations, even the weird stuff. And now, if we're checking all the paths, you know, we probably have some kind of bound on something, size of arrays, size of the input, number of loop iterations. And so we might be worried about that. Moreover, we might be worried about our own reasoning. We're looking at a program, and if we're just looking through all the paths and reasoning in our head, or reasoning in our head that these are all the paths, then you might be worried that you made a mistake in your own reasoning, and that's going to let bugs through. So to eliminate that cause of concern, gain more confidence the program is correct, you might want to upgrade from running the program and doing some kind of informal proof that you know, all the inputs will behave in a similar way. You might want to switch to actually using some kind of sound reasoning method. And you know, in the extreme, of course, this might be, you know, using a solver to, you know, check all of your logical specifications, or using proof assistant to check that your proofs are correct. but more likely what it means is some kind of static analysis of an abstract interpretation form. And that allows you to specifically write down the rules by which you reason about the program, check very carefully that the rules are correct, and then unleash those rules on a program who you don't trust yourself to reason about. So once you've gotten to this stage, you know that you are reasoning correctly about a program. You know you're not missing any kind of inputs. You're going down all the paths of the program. You're handling every possible input. You have a compelling description of what you want to achieve, a specification. And you can actually guarantee that using the sound reasoning method that you did. And then finally, at this point, we now have a complete confidence that certain properties of our program might be true. It could be array access, inbounds, it could be avoiding security leaks, it could be ensuring that certain kinds of transactions can't occur. And at this point, we can add more and more of these properties, each one giving us more confidence in our code. And eventually the leap from a long list of properties we've proven to a complete description of what the program ought to do, a complete functional specification that we have verified to be correct, isn't that big. And usually at this stage now, you're leaping to use a very powerful logical framework to do the reasoning. It's no longer enough to just use a couple of specific conditions on program states that you can string together. Now you actually want to know something about the full power of reasoning about arithmetic or arrays or the data structures in your code or security properties or whatever the case may be. And it's at this point that you're sort of mopping up all the remaining properties you need to discover by moving to a more powerful logic and integrating directly with a solver or a proof system of some kind. So questions about this sort of spectrum of software verifiedness and how you might go, the steps or the process in a real world program toward getting more confidence that it's correct, and how all this relates to the actual life of a software engineer.
How much of this path would you say you normally go down before your boss tells you to go to another project?
Well, I mean, it depends on your boss, right? There's some companies out there that don't do testing, and you can tell. I think this is a great question though, which is like, how far do you go? And you asked like, how far would your boss let you go? Which, you know, maybe you have a bad boss, but maybe your boss has a point, right? How far should you go down this path? How important is verification really? So I think different kinds of verification are essential for different kinds of programs, or really different pieces of your program. So for example, if you're talking about testing, you know that you're probably going to miss some bugs. But on the other hand, one of the great things about testing is it doesn't require writing a specification. It just requires writing this extremely loose thing, which is certain inputs should act in specific ways. And so testing, that might be the ideal way to test something like a user interface. A user interface, even if you get it wrong, it's probably not that big a deal. I say this with a bit of a strained look because, of course, my research is on verifying user interfaces. But nonetheless, most user interface bugs, they might lead to a user interface that's hard to use. It might be confusing, but many of your users will adapt. And furthermore, it's quite difficult to write down a specification for how should your user interface behave. Yes, some specific properties, it's quite easy to encode. Text shouldn't overlap. It shouldn't all be one color, etc. But it's basically impossible to write down a formal specification for should look pretty, or should draw the eye here, or users should click buy now. And so this is sort of the ideal place where you want to use a very lightweight form of testing. The cost of bugs isn't that high. UIs change frequently. So a heavyweight form of verification would just be too rigid. It's too difficult to write down a specification. So that's the sort of thing where we might use a very lightweight form of testing. Now, if you want to talk about something a little heavier weight, random testing, it's still not very difficult, but now you're looking at a place where you're a little more interested in bugs not coming through, and furthermore, it's somewhere where it's easier to write down a specification of what should occur. So here you might be looking at, for example, validation code. Validation code, it's pretty easy to describe what are you trying to test for, that this has a certain form, or like this is related to that in a certain way. The specification is relatively easy to write down. It's also relatively easy to generate random tests. And often validation has the benefit that the specification is shorter than the code you'd need to generate random inputs. So in this case, this is the sort of code, often any kind of filter or any kind of interface layer that can often be tested with random testing, specifically because you have a bit more of a sense of what the specification is. You have a bit more of a sense of, what it means for the code to behave correctly. And you're also a little more interested in avoiding bugs because they may actually cause problems in your code. Now, as you move down this process, as you move to more and more verification, you're talking about more and more essential properties, code that changes more and more infrequently. And you're also talking about stuff where the specification is becoming clearer and clearer. So maybe model checking is well applied to some specific domain logic. The domain of whatever your program is doing, whether it's calendars or course management on or it's logistics, or it's some kind of retail thing. The domain that your software is operating in is something that you understand fairly well. So it's a place where you can characterize the possible inputs, the possible situations that might occur. And it's also the stuff that when it goes wrong, it'll be, in some sense, it's most likely to go wrong in a way that's problematic in the domain itself. It's a problem for the things people actually care about. So that's a place where you can characterize the inputs. You can make sure that you check every possible situation, and where it's actually valuable to check all the possible situations, because you have some sense in the domain which situations are likely to come up and what the consequences might be. So you can see we've now kind of gone deeper and deeper into the program. We started at the top, the UI layer. Then we went one level deeper, where the UI is sort of forced to conform to whatever requirements the specification itself has. Now we're into the guts of the code itself. Now we've got the business logic that we need to understand. So, and that's been enabled by increasing rigidity, better understanding of the domain. Most of us are not design experts, and even those who are can't describe design formally, but you likely do know quite a bit about your domain and what it means to be correct in that domain. So let's keep going. Let's keep going sort of deeper into the program and see where more and more verification makes sense. So for example, symbolic execution, the fundamental idea is handling all the weird exceptional cases. Well, that's the place, this kind of error handling code, these kind of edge cases, side conditions that rarely come up. That's the sort of code that symbolic execution excels at checking, because the whole idea is check every path. And every path means all of them, including the ones that are unusual or rare, or you wouldn't think would come up, or it's hard to find an input that triggers it. So now we're in the error handling code. Now we've understood the exceptional cases, the unusual things that might happen to our code. And we can go further, for verifying properties of your code. Well, often, for property verification, you kind of want to reason about code that is in some sense simple. Because you want sound reasoning, and so you're going to be doing reasoning with a computer, and computers are kind of dumb, and it'd be a lot of work to teach it about some very complicated kind of code and how it works. But at the same time, you want code that's quite essential. You want code that needs to maintain certain properties for everything to work. And so glue code, that's often a place where you want to do some kind of property verification. You want to make sure that as stuff is shuttled from this component into this component, it said the post conditions of this one component ensure the preconditions of another, and you actually want to test that because it'll go in and out of various data structures. And so that sound verification is actually important because it's kind of hard to trace what's going on. And so now we've gotten, all the way down into the bottom, the mess, the pipework of the code. And so we're still not doing full verification. So like, what does it really make sense to do the full sort of verification you've learned in this class for? And a lot of that, a lot of time it's sort of the enabling platform for some software. Maybe it's a core algorithm. Makes sense to try to verify it if you're not sure it'll work. Maybe it's something like the compiler or the operating system where you're basically relying on it to be correct. And one of the reasons full verification works here is that you're often getting some aspect of leverage. You often have multiple applications that use the same platform. And so that verification, sure, it's a lot of work, but it also means a lot of code that you suddenly don't have to think about bugs in, a lot of user behaviors that you handle correctly. And if it's something as essential as like an operating system, you probably also have the benefit that the specification is well understood. A lot of applications have been written on top of this platform. A lot of different stuff has been done with this platform. The platform has made choices about how certain situations should be handled. And those choices you can reflect in a specification. So this is kind of, sorry to sort of overwhelm you, Skylar, with my answer. It's just that my next slide happened to be the answer to your question. But there's sort of a whole spectrum of different kinds of code within a single program. And across that spectrum, you also see the whole variety of different verification techniques, or we might say confidence boosting techniques. Pranav, you have a question?
Yeah, I was just curious, like, what would be the real life examples of softwares or operating system or compilers that are fully verified and that we come across daily?
Yeah, so that's a good question. I mean, there has been quite a number of essential pieces of code that have been verified correct. But it's usually not the version we use because there are secondary properties that we're trying to address. So for example, there is the security enhanced L4 kernel, SEL4. This is a operating system kernel with a complete proof of correctness. And this complete proof of correctness, it extends to the assembly layer. So you know that the specific binary you're running is correct. And the properties proven about this code are things like process non-interference, correct scheduling, ensuring that security properties are satisfied, making sure that the operating system will respond to various requests, system calls, in an appropriate and timely fashion so it doesn't get blocked. The CompCert compiler is used in some industries, specifically in aerospace. There is some use of CompCert. That's a compiler that's been proven to be correct in the sense that the compiled code does exactly what the input C code does. And we're now starting to see verified compilers for other languages as well. But CompCert was kind of one of the first and biggest. Those are all examples of real significant programs that have been verified, but at the same time, they're not code we execute every day. SEL4 is used. There are some commercial users of it. CompCert is used. There are some commercial users, but they are not Linux or GCC or Clang. What we're now seeing is subcomponents of actual real software adopting some fully verified components as well, basically as we've gotten better at verifying more realistic code, and as we've developed better and better understanding of how to verify code still, for example, performant. So you saw the implementation of crypto algorithms in the last lecture, and we've similarly, for example, in LLVM, the developers now use a verification tool to make sure that certain types of optimizations within LLVM are correct. So we are seeing a growing number of real world programs incorporate verified pieces as well. So for example, if you run Chrome, if you run Firefox, in either case, you're using a verified crypto library, right? And those are real world pieces of code. But of course, that verification doesn't extend to all of Chrome or even the network layer, or really even all of the crypto library. It just extends to the most essential parts of them. And that's what we're seeing now. And that's kind of what the spectrum idea is trying to demonstrate, that there are parts of the code you'll probably never verify because it just won't be worth it, and it won't even be clear what the spec is or what value you'd get out of verification. But at the same time, there's a lot of different parts of the code where it's useful to do some amount of verification or potentially more and more verification. You know, initially when I drew up this spectrum, I had a 7th box, which is this idea of interlocking verified systems. What if you verified not just a single program, but all of the software, and you prove that all of the interfaces matched up? That's something that researchers are starting to do. These efforts are, you know, most plausible on embedded devices. So if you have, for example, a pacemaker or a glucose, an insulin monitor, you probably actually have all of the code that runs on that device. And it's also important enough that you actually want to fully verify it. Probably the best example we've seen of verification successfully out there in the world for really big, really important software is not actually software, but hardware verification. The chips you buy today have gone through all forms of different kinds of formal verification, just because it is so insanely expensive to do a recall of a certain chip. And you know, in the last couple of years, we've seen a lot of news stories about bugs in chips. So there's always the question of what you verified. Did you verify the right thing? You know, cache side channels weren't something that Intel had been working on verifying. But on the other hand, we also haven't seen recurrences of, for example, the Intel FDiv bug, which for those who don't remember it, was the Pentium 4 implemented division incorrectly. And so since that time, Intel and AMD invested heavily in verifying their chips, specifically because it was, you know, so darn expensive to deal with bad chips. And so that's an example where, because the costs of failure are so insanely high, literally in the millions of dollars, or even hundreds of millions of dollars, you've seen full verification come in some sense the furthest. But I think also, as you're seeing software becoming more and more important, you're seeing people do more and more verification. I mean, the crypto implementation in your browser actually is probably at least hundreds of thousands of dollars worth of damage if that's incorrect and someone finds a way to exploit it. And more and more, as software becomes more important, verification of that software will also become more important, because bugs in the software will become more important. Other questions or comments about verification and its use in the real world? Okay, well, in that case, we're at the end of this course. I hope you learned something useful from it. It has been a pleasure to teach it. It has been a pretty weird semester, what with online lectures and being shut in at home and a worldwide pandemic going on. But thank you all for adjusting as best you can, handling all this rapid and chaotic change. I don't think this is how any of us expected the semester would go down, but I hope whatever your goals were for the class, they were mostly met. I've certainly had a lot of fun teaching it, and I hope it has been as useful to me as it was to you as it was exciting to me. One final thing that, other than of course the various remaining bits of assignment that you need to do, that I'd like to ask you to do is fill out the course evaluations. I know that every professor that you have is asking you to fill these out right now, and I also know that they are insanely boring. So I'm totally with you on all those fronts. Nonetheless, I am strongly encouraging you to fill out the course evaluations. Course evaluations are how we evaluate professors on their teaching. This might strike you as a weird way of doing it because y'all hate filling out course evals, and they also feel, you know, disconnected from your life and not a particularly good evaluation of how we're teaching. That's pretty much true, but for whatever reason is more or less the best we've got. So the course evaluations, in fact, play some role in tenure, in promotion, in pay. They take some role in the mentoring we get from other better teachers in our department. They play some role in understanding how the department allocates resources to its various classes. So the course evals are released. I have the URL for them on the screen. You can go and open the course eval website right now and fill them out. It takes a couple of minutes. I strongly encourage you to do so immediately because otherwise you will forget and then you will not want to do it because I admit it is pretty boring to do so. But this is the end of the class. It's pretty much all you've got left to do. So please fill out this course evaluation. I would love to hear either on the course eval or just in email if you prefer to do it that way. Any feedback you have on the class, anything you thought was should be done differently next year. We're always trying to tweak the class, make it more interesting and more useful. And we've actually made quite a few tweaks from the last time this course was taught. So looking forward to feedback and also strongly encouraging course evals. If you lose the URL, you can find it on the course website. I'll also be putting it on Canvas. You won't be able to escape it. Just do it now. And I believe if you do it now, you also see your grades earlier. So that can be an incentive. And so with that, thank you for being a wonderful class for this whole semester. I hope you enjoyed the class. You learned a lot that met your goals. So with that, I suppose I'll see many of you, or at least some of you, in future classes. I'm teaching a class on web browsers in the fall, but if not, hope you have a good rest of your academic and career, and then successful transfer of all that to your workplace. Yes, thank you to everyone saying thank you over the group chat. It is heartwarming to know that the class has been useful to all of you. And if you feel that way, do fill out the course evals. Yes, Hao-Chun?
Hi, I have a quick question. Like,
Mhm.
I'm at my final step, and I'm wondering how can I get the